our journey into the mystery of time challenges the very foundation of our understanding. What if time, as we experience it, is not an absolute, unchanging dimension, but instead an emergent phenomenon, or even an illusion shaped by our consciousness? Drawing insights from Einstein's relativity, quantum mechanics, and modern neuroscience, this exploration redefines time as a fluid construct, woven from the intricate interplay of matter, energy, and information. By questioning our deepest assumptions, we open the door to a new perspective, one where our perception of time may be a reflection of something far more profound and universal. Historical philosophical perspectives on time. Philosophical views on time from the past show a rich range of ideas that have changed over thousands of years, setting the intellectual groundwork for how we understand this mysterious dimension today. In ancient and classical cultures, time was not just a series of events. It was seen as an important part of how the universe works and how it changes. The famous pre-Socratic philosopher Heraclitus said, "Everything flows," Planetary, which means that the only thing that stays the same in the world is change. His ideas about time were closely connected to how reality was always changing. For example, fire, which stands for change, was used to represent how life was always changing. The idea of time being static, which would later come up in other philosophical systems, was very different from this one. Plato advanced these early ideas by introducing a dualistic framework that distinguished between the world of becoming and the eternal realm of forms. In dialogues such as the Timaeus, Plato suggested that the cosmos is governed by a divine order, a realm of perfect and immutable forms that the transient physical world strives to emulate. Time, in Plato's philosophy, was the moving image of eternity, a measurement of change that allowed the material world to participate, albeit imperfectly, in the perfection of the eternal. This conception implied that time is both real and illusory, real in its measurable experiential aspect, yet ultimately a reflection of a deeper, timeless reality that underpins all existence. When philosophical ideas moved into the Middle Ages and Renaissance, religious and spiritual beliefs started to mix with ideas about how time works. Medieval thinkers, who were affected by Aristotle, saw time as a continuum that was measured by change. They also gave time religious meaning. People thought that God made time, which went in a straight line from the beginning of time to the end of the world, but it had a divine purpose. People like St. Augustine wrote about their thoughts on time in works like Confessions. In this famous passage, he asks how time could exist if the past doesn't exist anymore, and the future hasn't happened yet. Augustine thought that time was deeply connected to how people remember, pay attention, and look forward to things. He stressed that time was both objective and subjective, and that it was set up by God. The Renaissance, on the other hand, saw the return of classical ideas, along with a rise in scientific research. Thinkers like Giordano Bruno and Nicholas of Cusa argued for an infinite, changing universe, instead of the standard, fixed view of time. Bruno, for example, thought that the world had no limits and was full of an endless chain of events that all fit together to make a big, living whole. In his mind, time, like space, seemed like an endless place where things could be made and changed all the time. Radical ideas like these were often met with opposition from the political and religious establishments of the time, but they were a big change from the limited mechanical world that medieval theologians had imagined. Transitioning into the early modern era, a dramatic shift occurred with the advent of the scientific revolution. Sir Isaac Newton's Principia Mathematica introduced the concept of absolute time, a steady, unchanging flow that exists independently of any external factors. For Newton, time was like a universal clock ticking uniformly across the cosmos, a framework that provided a fixed stage for the motions of celestial bodies. This view, though incredibly successful in explaining planetary motion and laying the foundations of classical mechanics, began to be challenged as new empirical evidence and theoretical insights emerged. Newton's idea of absolute time ruled the field of science for hundreds of years, but early signs of its flaws started to show. Observations that eventually led to Einstein's groundbreaking theories, like the fact that planets' orbits and light behavior can be different, suggested that time might not be a simple, linear progression. These findings led to a new look at the nature of time, which in turn led to the creation of the theory of relativity. During this time of change, logical thought went from seeing time as an absolute background to seeing time as woven into space, making up the fabric of space-time. This big idea challenged the idea that time is a constant that can't be changed. Instead, it suggested that time could be affected by things like speed and gravity. Scientific conceptions of time. Over the centuries, the study of time in physics has changed a lot. In classical mechanics, time was seen as a simple, almost intuitive idea. Today, time is seen as a multifaceted, very complicated reality. This section talks about how time is thought of in classical physics, how it is seen through the lens of thermodynamics and entropy, and finally how it has become an important part of current theoretical physics. In classical physics, time was considered as a constant universal parameter, an absolute backdrop against which all physical processes transpired. Isaac Newton famously described time as absolute, true, and mathematical, flowing equally regardless of the external conditions. Under Newton's paradigm, time was independent of the events it measured. It ticked away uniformly, providing a constant stage for the drama of physical motion. This notion aligned nicely with ordinary realities, where seconds, minutes, and hours looked set and reliable. Modern physics, which came out in the early 1900s, changed this way of thinking, though. Through Albert Einstein's theory of special relativity, space and time were joined together to form a four-dimensional stream called space-time. Time was no longer a separate thing. It was relative and changed based on how fast the viewer was moving. Experiments showed that for things going close to the speed of light, time could dilate, which means it could slow down. This wasn't just a theory. It has been proven by many tests, such as seeing subatomic particles move quickly and making accurate measurements with atomic clocks on fast-moving planes and satellites. Einstein's general relativity further deepened our understanding by showing that gravity also affects time. Massive objects, such as stars and planets, cause a curvature in space-time that results in gravitational time dilation. Clocks run slower in stronger gravitational fields, a phenomenon that has practical implications, for instance, in the operation of the Global Positioning System, GPS. Thus, while classical mechanics treated time as a simple, unvarying flow, modern physics reveals a dynamic interplay between time, space, and matter, a relationship that challenges our intuitive grasp of what time truly is. The study of thermodynamics added another level of complexity to our understanding of time at the same time that mechanics did. A core idea in thermodynamics is that energy flows and changes forms. The second law, which says that entropy, a measure of disorder or randomness, tends to rise over time in a single system, is one of its main ideas. This unstoppable change from order to chaos is what gives time its arrow, the direction that separates the past from the future. Classical mechanics uses symmetric time formulae, but thermodynamics shows that there is a deep-seated unevenness in time that is part of the way things work in the real world. The idea of entropy not only explains why things like combining, diffusion, and decay happen on their own, but it also gives us a statistical basis for how time's direction comes about. As systems change into states with more entropy, they move forward naturally, which seems to be what makes time move forward. Based on this knowledge, some scientists say that the arrow of time is not a basic trait of time, but rather a feature that appears when big groups of particles behave in a certain way. From this point of view, the way information and energy are spread out and how time seems to flow are closely connected. This means that the development of physical systems is inherently irreversible. The way that thermodynamics and information theory work together has also led to new thoughts about what time is and how it works. The thermodynamic arrow of time and the informational arrow of time are ideas that suggest how we see time may be deeply linked to how information is stored and lost in physical systems. As knowledge gets worse, the past becomes more set in the system while the future stays open, giving it a sense of direction that matches how we feel about time. It wasn't just relativity and physics that changed the way we think about time. In current theoretical physics, time is seen more and more as an emergent term, which means that it comes from more basic processes that don't depend on time. Quantum gravity researchers, for example, are looking into models where space and time are not fixed points in time, but rather come about when more basic elements interact and become entangled with each other. Loop quantum gravity and causal dynamical triangulations are two ways of looking at things that see time and space as big effects of quantum processes going on inside. At the Planck scale, the smooth, continuous fabric of space-time is changed to a discontinuous, granular structure. The known flow of time is seen as something that happens because of how these basic parts behave statistically. This emergent view of time dovetails with certain interpretations of quantum mechanics, where the measurement process seems to create a moment of time. The Wheeler-DeWitt equation, for instance, which arises in attempts to formulate a theory of quantum gravity, famously lacks a time variable, suggesting that time itself might not be fundamental. Instead, time may emerge from the relationships between quantum states as the universe evolves. In this framework, the conventional notion of time as an ever-present continuum is replaced by a more nuanced picture where time is reconstructed from the ordering of events and the correlations between them. The new ideas about time make us question not only how we measure it, but also what it really means. Is it just a parameter in our models? Or is it a trait that changes over time and describes how information flows and the universe's complexity grows? The most important area of study in theoretical physics and astronomy right now is looking at time as something that just happens. This is because scientists are trying to make a framework that combines quantum mechanics and the theory of relativity. Time in physics: Newtonian versus relativistic views. Newton widely explained his view of time in his famous work Philosophiae Naturalis Principia Mathematica. In it, he said that time moves evenly regardless of what is happening in it. Newton thought of time as a separate thing from the physical world. He called it a true, mathematical, and universal reality. This absolute time set a stable, constant stage for everything that happened in the real world. The equations of motion in Newtonian physics assume that time moves at the same speed for everyone, no matter where they are in the world or how fast they are moving. This idea was a big part of how exact estimates and calculations became what classical physics was known for. Absolute time had huge effects. It made it clear that the motion of things and the measurement of time were two separate things. This gave scientists a safe way to study the physics of motion, collisions, and the motion of the stars. This idea seemed to be supported by everyday things as well. For example, the ticking of a clock seemed to stay the same no matter where or how we were moving. Even though this model was good at understanding a lot of natural events, it started to fall apart as new facts came out that couldn't be explained by a smooth flow of time. Albert Einstein's theory of special relativity, which he came up with in 1905, changed the way we think about time. Einstein questioned Newton's ideas by showing that time is not fixed, but changes depending on how fast or slow a viewer is moving. Special relativity says that the speed of light stays the same in all inertial frames of reference. This has strange effects like making time go faster and making lengths shorter. When looking at things moving at speeds close to the speed of light, time seems to slow down compared to people who are standing still. Experiments with fast-moving particles and accurate atomic clocks have shown this to be true. Einstein had many more ideas that changed the world, not just special relativity. Einstein added to these ideas in his general theory of relativity by saying that gravity affects time as well. The theory of general relativity says that heavy things bend space-time, which means that time itself is twisted by gravity. Watches that are near a black hole or a very large star have stronger gravity forces than watches that are farther away. Clocks in these areas tick more slowly. Experiments and accurate readings from satellites in Earth's orbit have shown that gravitational time dilation is real. Einstein's work turned time from an object that didn't do anything or change into a part of the world that does things and changes. When time and space mixed, they made a four-dimensional continuum. How fast time moves depends on how fast the watcher is moving and how strong the gravity field is. Not only did these new ideas change physics, they also changed the way people think about time. They called into question ideas that have been around for hundreds of years about how time moves in a straight line. The ideas behind relativity have changed the way we think about time in many important ways. Newton's model said that time was an ever-present separate background, a universal clock that was always ticking, and this was taken for granted. But the discoveries of special and general relativity make us think again about this idea. If time can stretch, shrink, and even warp when there are strong gravitational fields, or when moving quickly, then our idea that time is steady and regular is put into question. Take the case of two clocks that are exactly the same, one on Earth and one in space, moving at a very slow speed compared to light. Relativity says that the clock on the spaceship would run slower than the clock on Earth. Experiments with fast-moving subatomic particles and precise measuring devices have shown this to be true. In the same way, imagine a scientist stationed near a black hole, where the pull of gravity is very strong. The astronaut's clock would move more slowly than a clock that was far from the effect of gravity. There is a strongly held belief that time is constant and universal. These thought tests and experimental findings force us to accept a reality where time can be changed and depends on the circumstances. If time is not a fixed thing but a relative one, then our ideas of the past, present, and future become less solid. The block universe theory, which comes from relativity, says that all points in time exist at the same time, and that time flowing is just a fiction. This view is very different from how we experience time passing. This makes me think deeply about free will, fate, and even the nature of life itself. Philosophers have long argued about whether the perceived passing of time is a real thing or something that people make up. As relativity shows, time can be stretched and squeezed. This supports the idea that time may be more of an emergent property than a basic building block of the world. Also, current technologies and science discoveries are based on the idea that time is relative. To make sure that satellite tracking systems work properly, for example, you have to take into mind the effects of time dilation that relativity predicts. Our technology keeps getting better, and these relativistic effects become more noticeable. This is real-world proof that our usual ideas about time need to be changed based on facts. Relativity and time dilation, special relativity, and the illusion of simultaneity. Since the speed of light doesn't change, time and space values must be changed so that everyone sees the same speed for light, even if they are moving at different speeds. It is this condition that directly causes time to stretch and length to shorten. A clock that is moving quickly compared to the viewer will tick more slowly than one that is still. Similarly, things that are moving will look smaller along the path they are traveling. These results aren't just interesting mathematical facts. They have been shown to be true in many experiments. For example, tests with fast particles in accelerators and studies of muon decay in the upper atmosphere both show that clocks that are moving do indeed run slower than clocks that are still. The relativity of simultaneity is one of the most strange effects of special relativity. In everyday life, we think that things that happen at the same time for one viewer happen at the same time for everyone else. Einstein's work, on the other hand, shows that simultaneity is not a fixed idea. In a moving frame compared to a still frame, two events that happen at the same time in one frame may not happen at the same time in the second frame. There are differences in how time is recorded that can cause the order of events to change as the speed of the witness goes up. As it turns out, time and space are basically connected. The distance between events in time depends on how fast or slow an observer is moving. Just like the distance between events in space depends on how fast or slow an observer is moving. To illustrate, imagine two lightning strikes hitting the ends of a moving train. For an observer standing on the platform, the strikes may appear simultaneous. However, an observer on the train, moving relative to the platform, might see one strike before the other, as the light from the strike nearer to the front of the train has less distance to travel to reach them. This simple thought experiment, often attributed to Einstein, underscores how motion can warp our perception of time. The illusion of simultaneity, therefore, emerges not because events themselves change, but because the framework we use to measure time shifts with our motion. With their huge effects, the postulates of special relativity made scientists and thinkers rethink what time is and how it works. In Einstein's theory, time is no longer a set, outside factor. Instead, it is a relative, changing quantity that can get longer or shorter based on the speed of the observer. This means that the flow of time is not the same for everyone. It changes depending on how fast something is moving. These effects aren't very noticeable in everyday life, where speeds are much slower than the speed of light. However, as speeds get closer to relativistic levels, the effects become more noticeable, which goes against our natural belief that time moves in a straight line. These postulates also have effects that go beyond individual viewers. They want a new way to think about how the world works, one in which space and time are combined into a single four-dimensional line called space-time. From this point of view, events are described by where they are in space and time, not just those places. Being able to see how the differences between the past, present, and future are blurred by relative motion gives us a more complete picture of reality. Einstein's ideas have very important philosophical effects. They disagree with the idea that there is a single objective now and say that what we think of as the present moment depends on our point of view. This makes me think about some important things about how we experience time. If simultaneity is relative, then is the flow of time just an illusion caused by our narrow view? A lot of thinkers and physicists today say that the way we feel time passing might just be a cognitive creation that comes from how our brains process sensory information in a world that is always changing. Time dilation at high speeds. Einstein's special relativity predicted that time would slow down, which is one of the most interesting things about it. This slowing down happens most dramatically when things get close to the speed of light. We usually think of time as a steady flow. But this effect, in which time seems to slow down for a moving object compared to a fixed viewer, makes us think again. In this section, we'll look at the math behind time dilation. Look at proofs from particle accelerators and cosmic ray studies, and talk about what this means for the future of fast travel. At the heart of time, dilation is the Lorentz factor, defined as gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v represents the relative velocity between observers and c is the speed of light. This factor quantifies how much time stretches for an object in motion. For instance, if an astronaut travels in a spacecraft at a speed where v is a significant fraction of c, the astronaut's onboard clock ticks slower by a factor of gamma compared to a clock on Earth. When v is much smaller than c, gamma is nearly 1, and time dilation effects are negligible. However, as v approaches c, gamma increases dramatically, causing the moving clock to slow down significantly, a prediction that, while counterintuitive, has been robustly confirmed by experiments. The discovery of muons is one of the oldest and strongest pieces of proof for time dilation. Cosmic rays hit the Earth's high atmosphere and make muons, which are unstable subatomic particles. Since muons have a known half-life when they are at rest, they should break down a long time before they hit the ground. Time dilation, on the other hand, makes their perceived lifetimes much longer in Earth's frame because they are moving at very fast speeds, often very close to the speed of light. Since this happens, a lot of muons reach the surface, which is exactly what special relativity says should happen. This finding is a natural experiment that proves that things moving at relativistic speeds do slow down time. Particle accelerators offer another compelling demonstration of time dilation. In facilities such as CERN's Large Hadron Collider, particles are accelerated to speeds very near that of light. Under these conditions, the particles' lifetimes are observed to increase significantly compared to their lifetimes at rest. Experimental measurements have repeatedly confirmed that the decay rates of these particles match the time dilation predictions derived from the Lorentz transformation. These controlled experiments provide not only direct evidence of time dilation, but also a quantitative understanding of how time stretches as a function of speed. In addition to being able to be proven by experiments, time dilation has huge effects, especially when you think about the future of high-speed flight. As people think about trips between stars, the relativistic effects that special relativity predicts become more important. Time dilation could make astronauts' trips much shorter than those of people on Earth if they are in spaceships moving at a speed that is a large fraction of the speed of light. For example, a trip that seems like it would take decades from Earth might seem like it only took a few years to the people who are taking it. This effect, which is often shown through thought experiments like the twin paradox, shows how time dilation could change long-distance spaceflight, giving us an intriguing chance to get past the huge gaps in time and space in the universe. The mathematics of time dilation also introduces us to the relative nature of simultaneity. As objects move at high velocities, not only does time slow down, but the very sequence of events can change depending on the observer's frame of reference. What one observer perceives as simultaneous events, another, moving at a high speed, might see as occurring at different times. This breakdown of absolute simultaneity reinforces the idea that time is not an independent backdrop, but is deeply intertwined with the motion and perspective of the observer. Even though there is a lot of evidence for the idea of time dilation, it goes against what we think we know about time. In normal situations, time seems to move steadily and evenly, but when there is very high speed or heavy gravity, this impression is broken. There has been a lot of intellectual discussion about this difference between what we feel and how time is relative. Some people say that the way we normally think about time is a cognitive construct, something that comes from the way our brains work. They say that relativity shows that time is actually much more open and changeable. These arguments continue to spark study that brings together physics, philosophy, and brain science. Gravitational time dilation. General relativity completely changed the way we think about time by showing that it doesn't move in a straight line across the universe, but is affected by mass and energy. Albert Einstein's theory of general relativity says that heavy things bend the fabric of spacetime. Because of this curve, clocks in stronger gravitational fields tick more slowly than clocks in lighter fields. This is called gravitational time dilation. The warping of spacetime is so strong near huge objects like planets, stars, and even more strange things like black holes and neutron stars that time seems to move more slowly. The speed of time can be very different from what we experience on Earth in places with strong gravitational pull. Einstein's field equations, which show how the shape of spacetime is related to the spread of mass and energy, led to this discovery. The idea is that time is not a fixed outside factor, but rather a moving number that changes based on how strong the gravitational field is. Near black holes, you can see a striking example of how gravity can slow down time. When these very dense things are close by, their gravitational pull is so strong that it dramatically bends reality. From far away, it looks like time slows down a lot near the event horizon. Time seems to slow down so much that an object falling into a black hole seems to stop at the horizon and never really go away. A lot of theory and practical research has been done on this strange effect that comes from the extremely curved shape that general relativity predicts. In the same way, neutron stars, which are the remains of huge stars that have exploded in supernovae, have strong gravitational forces that slow time down. Observations of pulsars, neutron stars that spin very quickly, show that time is stretched by gravity because the strong gravitational environment they live in changes the timing of their waves. There is proof for gravitational time dilation in the real world that is not limited to the strange worlds of black holes and neutron stars. The effects of gravitational time delay are very important in everyday technology. For example, atomic clocks on satellites in orbit around the Earth are used by the Global Positioning System, GPS. The gravity field around these satellites is smaller than around clocks on Earth's surface, so they tick faster. General relativity correctly projected that there would be a time difference. If engineers didn't take this into account, the system's positional accuracy would quickly drop, causing mistakes of several kilometers. Using exact atomic clocks at different heights and performing tests that have repeatedly proven the predictions of gravitational time dilation has given Einstein's theory strong support in a real-world setting. Gravitational time dilation has effects that go far beyond these cases. They go against our most basic beliefs that time moves in a straight line, showing that time is a flexible and changing part of our world. Let's say there are two identical clocks, one at the bottom of a deep mine and the other on the top. The clock in the mine will run a little slower than the one on the surface because of the stronger gravitational field beneath. Modern atomic clocks can tell the difference. This easy but profound proof shows that the passing of time is not a global constant, but rather a local event that is affected by the way space-time curves. Beyond the practical applications and observational confirmations, gravitational time dilation also raises intriguing philosophical questions about the nature of reality. If time is fundamentally altered by gravity, then our everyday experience of time may be just one facet of a more complex, multidimensional reality. This perspective invites us to reconsider how we measure and perceive time, as well as the implications for our understanding of the past, present, and future. Philosophers and physicists alike are compelled to explore whether our perception of a flowing time is merely an emergent property of our position within a gravitational field, or whether it reflects a deeper, intrinsic aspect of the universe that remains to be fully understood. Studying how gravitational time dilates has led to theoretical research into the most extreme situations where common sense doesn't work. In order to bring general relativity and quantum physics together, scientists are looking into how time might behave in situations where quantum effects and gravity effects are both important. The goal is to come up with a theory of quantum gravity that makes sense. In this theory, space-time is not seen as a smooth, continuous cloth, but as a structure that is made up of individual events and random chance at the smallest scales. This kind of study could finally shed light on the basic nature of time, showing whether it is a continuous variable or a phenomenon that appears from deeper quantum processes. Experimental evidence and technological applications. Einstein's ideas are supported by a lot of strong evidence, and the proof for time dilation comes from both natural events and controlled lab experiments. Several exact tests have shown that time does slow down for things that are moving or in strong gravitational fields. This changes the way we think about time in a basic way. Researching cosmic muons led to one of the first and most well-known proofs. When high-energy cosmic rays hit the Earth's atmosphere, these subatomic particles are made. When muons are at rest, their half-life is very short, about 2.2 microseconds. But because they are moving so fast, often close to the speed of light, time dilation makes their half-lives much longer from Earth's point of view. Because their lifetimes are longer, many muons can reach the surface of the Earth before they break down. This is direct proof that time moves faster for particles. Laboratory experiments have further substantiated these findings. Particle accelerators, such as those at CERN, accelerate unstable particles to speeds very close to the speed of light. Measurements of these particles' decay rates consistently show that their lifetimes are extended in accordance with the predictions of special relativity. These controlled experiments have not only validated the mathematical formulations of time dilation, but have also provided an accurate numerical basis for the Lorentz factor, the parameter that quantifies the degree of time dilation at a given speed. Modern atomic clock studies have pushed the limits of how precisely we can measure time dilation beyond these uses. Parts per quintillion can be used to measure time with atomic clocks that use the movements of atoms like cesium or ytterbium. It is possible to measure changes in the rate at which time passes when these clocks are put at different heights, like one at the top of a mountain and another at sea level. This further supports the idea that time slows down because of gravity. Because even small changes in Earth's gravitational potential can be seen to cause changes in clock rates, these studies have given us some of the most accurate tests of general relativity. The technological applications stemming from our understanding of time dilation have revolutionized various fields. In addition to satellite navigation, advancements in precision timekeeping have critical implications for telecommunications, high-speed financial trading, and the synchronization of power grids. Modern digital systems rely on coordinated timing signals, and the ability to measure time with extreme precision ensures the reliability and efficiency of these systems. Furthermore, time dilation effects are central to the development of experimental techniques in high-energy physics, where controlling and predicting the behavior of particles at relativistic speeds is crucial. These scientific proofs and technology uses also change how we think about time in a larger sense. They question the idea that time is an absolute background that doesn't change. Instead, the data shows that time is changing and relative, and that both speed and gravity shape it. This new understanding makes us rethink how we normally experience time, which seems set and unchanging. Instead, we should see time as more complex, changing shape based on how we look at it. These kinds of discoveries have very important philosophical implications. They say that how we feel about time might only be one part of a much bigger and more complicated event. They say that it's like a tapestry made of our inner experiences and the outside relativistic nature of the world. In addition, the fact that time dilation has to be taken into account in technology systems like GPS supports the idea that even physics ideas that seem abstract can have real-world effects. It shows that the statements of special and general relativity that don't make sense aren't just in theoretical physics, but are strongly rooted in how modern society works. We can measure and use these effects very accurately, which shows how reliable Einstein's theories are. It also connects the abstract mathematical ideas of relativity to the real-world experiences we have. Time in the cosmos. How time functions on other planets. Time is not measured and experienced the same way everywhere in the world. Instead, it is greatly affected by the features of each planet and its unique orbital and environmental conditions. The way we think about time on Earth is shaped by the way the world spins on its axis and moves around the Sun. There are, however, a lot of interesting differences in how time is experienced or counted on other planets, whether they are hard physical worlds like Mars or the gas giants in our solar system. This part looks at how the spinning and orbital periods of planets set local time. It also compares the time cycles of different planets and thinks about how their different settings might affect how people who live there might sense time. The simplest way to think about a day on any planet is as the amount of time it takes for the world to make one full turn on its axis. This time period lasts about 24 hours on Earth, which sets the tone for our daily routine. On other planets, though, this time of spin can be very different. For example, Mars rotates once every 24.6 hours, which is a lot like Earth's day. However, even small changes can have big effects on the planet's climate and on when possible human trips could happen. While Venus, on the other hand, is an even stranger case. Venus rotates very slowly and backwards. It takes about 243 Earth days to make one turn, which means that its day is longer than its year, which lasts about 225 Earth days. The big differences test our usual ideas of what a day is and make us rethink how time would be organized in a society that lived in such a world. The orbital period of a planet, the time it takes to complete one orbit around its star, plays a crucial role in determining the length of its year. Earth's year, defined by its orbital period around the Sun, is 365.25 days, a figure that underpins our calendar system. On the other hand, the gas giants, such as Jupiter and Saturn, have significantly longer orbital periods due to their greater distance from the Sun. Jupiter, for instance, takes about 12 Earth years to complete one orbit, while Saturn takes roughly 29.5 Earth years. These differences not only affect the astronomical calendar, but also influence seasonal cycles, climate patterns, and potentially the biological rhythms of any life forms that might exist on those planets. When you compare global time on different worlds, you can really understand how different time could feel in different parts of the universe. The short rotational period and middling orbital period on Earth make for a healthy climate that is good for life as we know it. The regularity of the day-night cycle has changed biological processes like circadian rhythms, which affect how people sleep, how hormones work, and even how environments act. On the other hand, Mars has slightly longer days and similar weather changes because of its orbital period. This means that human travelers would have to change how they keep track of time and their daily routines to fit a Martian soul, which could be hard because of how we are used to keeping track of time. The gas giants, with their enormous rotational and orbital periods, paint an even more radical picture. Although these planets do not have solid surfaces, their atmospheric bands rotate at different speeds, creating complex temporal patterns. For any hypothetical inhabitants or observational phenomena in the upper atmospheres of these planets, the concept of time might be dominated by chaotic multi-layered cycles rather than the steady, predictable rhythm experienced on Earth. Such environments would likely foster completely different biological and physical processes, where the flow of time is perceived in cycles that could range from very short bursts in localized storms to exceptionally long periods governing the planet's overall evolution. The different gravitational pulls on these worlds change how time is kept. Einstein's theory of general relativity says that when gravitational forces are greater, time moves more slowly. This is called gravitational time dilation. While these effects aren't very strong on worlds with average masses, time would move a little more slowly in places with stronger gravity, or on things with higher masses. So, on a huge gas giant with strong gravitational differences, the passage of time could be very different in different layers of the atmosphere or at different latitudes. This change adds to the complexity of planetary time, which is already very different. In addition to physical measures, a planet's surroundings can have a big effect on how people think about time. It's hard to tell the time on Earth because of things like the sun rising and setting, the changing of the seasons, and even social norms like work plans and holidays. These clues might be very different in other worlds, which could change how time feels. For example, on a world with a very long day, the longer time of daylight might mess up the circadian rhythms of any local animals or human explorers, which could cause changes in how they sleep, how their metabolism works, and how their brains work. On the other hand, a world with a very short day might need biological processes to change quickly, making it seem like time moves faster than on Earth. The interplay between a planet's climate, its atmospheric composition, and its orbital dynamics can also create unique temporal environments. In regions where extreme weather events are common, such as the turbulent storms observed on Jupiter, the rapid, chaotic changes in weather might make time feel fragmented or episodic. Alternatively, a planet with a stable, unchanging climate might foster a perception of time that is slow and meditative, where change occurs so gradually that it is almost imperceptible. Time in cosmic expansion and the Big Bang. The beginning and development of time are closely linked to the past of the universe. Time began in the chaos of the Big Bang and changed as the universe grew. Modern physics says that time didn't exist the way we know it before the Big Bang. Instead, it came into being at the same time as space, as the universe began to expand very quickly. This part talks about how time can be seen as something that formed in the very beginning of the universe. It also talks about the role of inflation in stretching and changing time, and it looks at the evidence from the cosmic microwave background, CMB. Normal ideas of time don't work before the Big Bang. There is no clear line between before and after, because time is something that comes from the way the world changes over time. The universe started about 13.8 billion years ago, with a very high density and temperature. This is called the Big Bang. It is thought that the normal structure of space-time was very unstable and unclear in this early state. As the universe grew and cooled, an organized space-time formed. This gave us the idea of time as we know it today, which is the order of events. This idea of time as emergent says that what we think of as a constant flow of time is not a basic background, but a large-scale effect that comes from the way the universe works. In a sense, the arrow of time, the unstoppable flow from the past to the future, is not something that was built into the universe at the start. It is something that forms as the universe changes, and its starting conditions create complexity, structure, and chaos. The idea of cosmic inflation is one of the most important steps forward in our knowledge of how the universe came to be. Inflation says that the universe went through a short time of exponential growth, just a fraction of a second, after the Big Bang. This fast stretching of space-time not only made it possible for the large-scale structure we see now, but it was also a key part of how time changed over time. During inflation, quantum changes that were already present in space-time were sped up to astronomical levels. This started the process of galaxies and other cosmic structures coming together. It's also important to note that inflation changed how time is counted on a cosmic scale. The very large growth stretched the time gaps, making the time dimension more even and smoothing out the bumps in the new universe. So inflation was the way that the early universe could change from a state of chaos and changeability to a state of order and structure on a big scale, where time is a well-defined measure. It's possible that the early universe's quantum state would have changed very little without inflation. This could have caused a very different, less ordered world where time would be much less stable and predictable. The cosmic microwave background, CMB, offers one of the most direct windows into the early universe and serves as a critical source of observational evidence for our understanding of cosmic time. The CMB is the residual thermal radiation from the Big Bang, now cooled and stretched by the expansion of the universe to microwave wavelengths. Detailed measurements of the CMB, particularly through satellites such as COBE, WMAP, and Planck, have revealed tiny fluctuations in temperature across the sky. These fluctuations are the imprints of the primordial quantum fluctuations that were magnified during inflation, and they provide vital clues about the initial conditions of the universe, including its density, composition, and the scale at which structures began to form. The patterns seen in the CMB not only back up the inflationary model, but they also help us figure out how the universe evolved over time. The fact that the CMB is the same over very long distances suggests that the universe was once in a state of almost perfect temperature balance. This suggests that space and time came from the same place. Also, the small differences in the CMB show the beginnings of the structure of the universe. These are the places where matter came together to make stars, galaxies, and groups. The cosmic web and large-scale time variability. The cosmic web is a huge network of galaxies, galaxy clusters, and dark matter strands. It not only gives us an amazing look at how the universe is structured on a big scale, but it also gives us interesting ideas about how time might change on different cosmic scales. As the universe changes, the gravity forces that shape these structures can cause small changes in the speed of time. This creates a fascinating area of study where astronomy meets the nature of time variation. The question of how galaxy structures change over billions of years is at the heart of this research. Under the pull of gravity, galaxies grow, change, and join within the cosmic web. Not everywhere in the universe is this moving process the same. According to general relativity, places where there is a lot of matter, like galaxy groups, have stronger gravitational forces. This can make time move more slowly than in places where there is less matter. For instance, in a densely packed cluster, the gravitational pull of nearby galaxies and dark matter can make spots where time moves much more slowly than usual compared to the rest of the universe. As these structures change and interact over cosmic time, the changing gravitational potential causes differences in the speed at which time moves in different places. These differences leave a subtle mark on the fabric of space-time that is unique to the cosmic web. Dark matter and dark energy play pivotal roles in these processes. Dark matter, which forms the scaffolding of the cosmic web, creates gravitational wells that attract visible matter into filaments and clusters. In these high-density regions, time dilation effects become more pronounced due to the stronger gravitational field. Meanwhile, dark energy, the mysterious force driving the accelerated expansion of the universe, acts in opposition by pushing matter apart, leading to regions where gravitational effects are weaker. The interplay between these two components creates a mosaic of cosmic environments, each with its own distinct gravitational profile and, by extension, its own local clock that ticks at a slightly different pace. Thus, the cosmic web is not just a structural network, but also a dynamic, time-variable system where the passage of time itself is modulated by the distribution and evolution of mass and energy. The growth of the universe may also have an effect on changes in the flow of time across cosmic structures. The measure of time can change as space itself grows, based on how curved space-time is in that area. In voids, which are large, mostly empty spaces between filaments, time moves more easily, maybe even a little faster, because of the lower gravity potential and lower density compared to areas within filaments and clusters, which are more crowded. In a way, this is like how clocks tick at different speeds in different gravity potentials on Earth, such as at higher elevations compared to sea level. These changes are very small on a human level, but they add up over billions of years and could affect how cosmic structures change over time and how time flows in the universe as a whole. Observational evidence for such large-scale time variability remains a frontier of modern astrophysics. While direct measurements of time dilation on cosmic scales are challenging, indirect evidence comes from detailed mapping of the cosmic microwave background, CMB, and the distribution of galaxies. The slight anisotropies observed in the CMB provide clues about the early gravitational potential fluctuations, which set the stage for the later evolution of the cosmic web. In turn, the distribution of galaxies mapped by surveys such as the Sloan Digital Sky Survey, SDSS, reveals the intricate web-like pattern of matter in the universe, hinting at the underlying gravitational dynamics that could cause differential time flow. Numerical simulations of cosmic structure formation further support these ideas. Advanced computer models that simulate the evolution of the universe from its early stages show how matter clusters into filaments and nodes under the influence of gravity. These simulations, which incorporate both dark matter and dark energy, allow researchers to explore how gravitational potentials vary across the cosmic web and to predict the resulting differences in time dilation. By comparing these theoretical models with observational data, scientists hope to refine our understanding of how time might vary across different cosmic environments. Time in extreme environments. It's strange how time bends and stretches in the universe compared to our daily lives. Time seems to slow down, speed up, or even stop in places where gravity is very strong, energy is very high, and motion is very close to the speed of light. Knowing how time works in these situations tells us things about the universe that we didn't know before and makes us question what reality is. Near a black hole, time behaves in ways that seem almost impossible. If someone were to approach a black hole's event horizon, an observer far away would see them moving slower and slower as they got closer. It would appear as if they were frozen in place, never truly falling in. However, this effect is not instant. Depending on the black hole's size, an outside observer may see the falling object move for quite some time before the slowdown becomes noticeable. This is because time dilation increases gradually, becoming most extreme right at the event horizon. Neutron stars, the incredibly dense remnants of massive stars, also warp time significantly. They are so compact that a mass greater than our Sun is packed into a sphere just 10 kilometers across. This immense density creates strong gravitational fields, slowing down time for anything near them. Pulsars, which are fast-spinning neutron stars, act as cosmic clocks by emitting pulses of radiation at precise intervals. However, the powerful gravity of neutron stars alters these pulses slightly, causing tiny shifts in timing. By studying pulsars, scientists can measure how time is distorted by gravity on smaller scales than black holes. Time doesn't always slow down in harsh settings. In parts of space where there is almost no gravity, like deep intergalactic space, time actually moves faster than on Earth. There is a real but faint effect here. There is a special mix of time effects that astronauts on the International Space Station experience. Because they are moving very quickly around the Earth, special relativity makes time slow down a little. But because they are farther from Earth's gravity than people on the ground, time moves a little faster for them as well. These two impacts almost cancel each other out, but astronauts really do age a tiny bit faster than people on Earth's surface. It's interesting that not all black holes change time in the same way. Near their event horizons, supermassive black holes that are millions or even billions of times the mass of the Sun don't make as strong of tidal forces as smaller black holes do. If someone fell into a small black hole, their head and feet would be violently pulled apart before they even got to the event horizon because of the difference in gravity. A supermassive black hole, on the other hand, has a much weaker gravitational pull near the event horizon. This means that a person could cross it without being torn apart, but time would slow down a lot. From the outside, it looks like they're going to stop moving forever. Space and time are warped so much around black holes that they cause strange visual effects. When something goes into a black hole, it doesn't disappear right away. Instead, the light from falling objects stays around longer because of time dilation, making it look like things are hanging at the event horizon. Some scientists think that this light that stays around could make a glowing ring around black holes, which would explain some of the things that the Event Horizon Telescope has seen. It's possible that what we see when we look into a black hole is not the black hole itself, but rather a collection of matter stuck in time just outside its edge. It was also different in the early world when it comes to time. It was much denser and hotter when the universe was young, so the effects of gravity and energy were much stronger than they are now. Some experts think that time may have worked differently back then, which could have changed how cosmic structures formed. The cosmic microwave background, which is made up of radiation left over from the Big Bang, has weak signs of this changed flow of time that show how time has changed over billions of years. Not only gravity, but also magnetic fields and energy flows can affect time in subtle ways. Magnetars, which are neutron stars with the strongest known magnetic fields, create some of the most intense environments in the universe. These magnetic fields are so powerful that they can distort space itself, potentially influencing the way time behaves near them. The interaction between magnetic energy and relativistic particles may cause time distortions that are not yet fully understood. This suggests that time may be affected by more than just gravity, opening up new possibilities for how it behaves in the universe. When high-energy particles move very close to the speed of light, they cause another strange reaction. Cosmic rays are particles that are thrown through space by events like supernova blasts. They experience very slow time dilation. From their point of view, their trip may only last a few seconds, even if it goes across huge cosmic distances. Some particles that hit Earth's atmosphere should break down in microseconds, but they stay alive for a lot longer than thought. Why? Because they are moving so fast, time seems to move more slowly to them, which lets them live long enough to reach the surface of Earth. Quantum physics makes time in very cold places even more mysterious. Some ideas say that time isn't smooth and continuous, but instead is made up of very small separate ticks that happen all the time. It makes us think about how we think about time and suggests that what we think of as time moving smoothly might actually just be a big illusion. Theories like loop quantum gravity and string theory say that time might act in ways we can't yet measure or understand when things are at their most extreme in space. Time distortions are not just thoughts from far away. Tests on Earth have shown them to be real. Scientists have put very accurate atomic clocks at different heights to find out how much time changes because of gravity. Even small changes in gravity can make clocks tick at slightly different rates when they're only a few centimeters apart. Even though these effects are very small compared to those near black holes or neutron stars, they show that time dilation is a real thing in the world and not just an idea. Time travel theories and paradoxes, theoretical foundations of time travel. People have been interested in time travel for a long time, and the theories behind it have changed a lot since modern science came along. At the heart of modern talks about time travel is the idea that time is not a fixed linear line, but is instead woven into space in a four-dimensional cloth called space-time. Einstein's theories of special and general relativity presented this idea, which makes it possible to think of time as a dimension along which one could, at least possibly, move. Einstein's special relativity proved that time is relative and that how fast time goes by depends on how fast the viewer is moving. This discovery led to the idea of time dilation, which means that clocks that are moving very quickly tick more slowly than clocks that are not moving. This event is well known in the field of particle physics, and it also provides a basis for more fanciful thoughts about traveling through time. This idea is often shown by the famous twin paradox. If traveling at relativistic speeds can slow down time, then traveling at those speeds might let someone experience time differently than someone who is fixed. General relativity further expands on this idea by demonstrating that gravity itself can warp time. Massive objects, such as stars and black holes, curve the space-time around them, causing time to run slower in stronger gravitational fields, a phenomenon known as gravitational time dilation. The implications are profound. If one could harness or navigate these regions of extreme gravity, it might be possible to exploit these differences in time's flow. Theoretical constructs such as closed time-like curves, CTCs, emerge naturally in certain solutions to Einstein's field equations. CTCs are paths through space-time that loop back on themselves, suggesting that under the right conditions, an object could travel along a path that eventually returns it to its own past. General relativity also makes some interesting predictions about wormholes, which are like shortcuts through space-time. In these models, a wormhole is a tunnel-like object that connects two faraway places in space-time. If they could be crossed, wormholes might make it possible to quickly get from one part of the world to another, and by extension, they might let you go to the past or the future. However, making or maintaining a wormhole that can be traversed is very difficult from a technical point of view. Researchers who study theories say that strange types of matter with negative energy density might be needed to keep a wormhole open. Even though this kind of strange matter hasn't been seen in nature yet, theoretical physicists are still very sure it exists. Mathematically, these ideas are explored through solutions to Einstein's equations. For instance, the Kerr metric describes the space-time around a rotating black hole and predicts regions where CTCs could, in principle, exist. Similarly, the Morris-Thorne metric provides a framework for conceptualizing a traversable wormhole. These mathematical models, while highly idealized, offer critical insights into the conditions under which time travel might be conceivable within the laws of physics. They also raise profound questions about causality, and the structure of space-time, questions that continue to be explored by both physicists and philosophers. Even though these models are very well made, there are still big academic problems to solve. One of the main problems is that some energy conditions that are usually taken for granted in general relativity are not met. These energy conditions make sure that matter acts in a way that makes sense from a physical point of view. However, they are not always met in the strange arrangements needed for wormholes or CTCs. Because of this, some scientists think that nature might stop people from making time machines through a chronology protection process that we don't fully understand. Stephen Hawking was the first person to make this famous suggestion. Chronology security says that quantum effects might step in to stop time travel that could cause problems, like the famous grandfather paradox, where actions done in the past could stop the time traveler from existing. On top of that, the mathematical idealizations that are used in these models often don't work when the real world is looked at. Theoretical ideas and the messy facts of astrophysical settings are very different. This means that even if CTCs or traversable wormholes are mathematically possible, they might be physically impossible for us to create with the technology we have now. In spite of this, the ideas behind time travel continue to spark new ideas and trial plans that aim to push the edges of what we know about time. Common paradoxes and their implications. Time travel ideas are interesting from a mathematical point of view, but they always run into problems that make us question what causes what and how reasoning works. Many people are familiar with the grandfather paradox, which is when someone travels through time and stops their own ancestors from existing. This makes them not exist. This paradox shows very clearly the logical problems that can happen if you think that things that happened in the past can be changed at will. In answer to these kinds of problems, many possible solutions have been put forward. The idea of self-consistency is a common one. It says that any actions a time traveler takes in the past must be in line with the path that leads to their original exit. From this point of view, things work together to avoid paradoxes. What might look like a chance to change the past ends up bringing about outcomes that are already part of history. The bootstrap paradox is another interesting paradox. In this one, an item or piece of information is sent back in time and gets stuck in an endless loop with no clear beginning. For instance, let's say that a scientist gets specific plans for a time machine from their future self. They build the time machine using these plans, and then they send those exact plans back in time. Because of this circular chain of events, the plans don't really have a starting point. We don't fully understand cause and effect until we come across puzzles like these. They make us wonder if the very idea of a beginning can make sense for events that are part of a closed causal loop. Causal loops and closed time-like curves, CTCs, are not merely philosophical curiosities. They emerge as legitimate solutions in Einstein's field equations under specific, albeit exotic conditions. However, these solutions come with their own set of challenges. The idea that the future could influence the past, or that events could loop back on themselves, upends our conventional understanding of linear time. This raises profound questions about free will and determinism. If every action is part of a self-consistent loop, to what extent do individuals possess the freedom to choose? Some physicists and philosophers argue that if time travel were possible, the universe might enforce a kind of chronology protection, as suggested by Stephen Hawking, to prevent the occurrence of paradoxes. According to the chronology protection conjecture, quantum effects might act to destabilize any configuration that would allow for time loops, effectively ensuring that any attempt to create a paradox is thwarted by the laws of physics. The philosophical debates about these riddles also touch on the structure of time and cause and effect. If things that happen in the present, the past and the future are connected in a way that lets the future change the past, then our normal idea of cause and effect might need to be changed. Some thinkers believe in an endless or block universe in which all places in time exist at the same time and the flow of time is just a trick of the mind. In this view, The problems of time travel are explained by the fact that going back in time doesn't change history, it just shows how rigid the four-dimensional space-time manifold is. However, this model brings up its own questions about what change is and how we feel the passing of time. Time travel theories face more interesting problems than just these well-known puzzles. Take the idea of parallel or multiple periods as an example. Some readings say that trying to change the past might only lead to the creation of a new timeline, which would avoid any problems that might arise in the first timeline. By saying that all possible events happen in different universes that don't interact with each other, this multiverse method gets around the logical problems. Some theorists like this idea, but it brings up the problem of how to prove that these other realities exist. It also raises the philosophical question of whether a branching universe really solves the original paradoxes, or just moves the problem to a higher level of ontological reality. These puzzles have a lot of different meanings. They make us think about the chance that our natural, linear view of time might not be enough to explain a world where time travel is possibly possible. Philosophers and scientists have had to rethink the basic ideas of free will, causality, and the structure of time in order to solve these problems. The paradoxes serve as a warning that our present theories of time travel can be mathematically consistent in some idealized situations, but it is still very hard to make these models fit into the real world. Also, the arguments about these paradoxes aren't just intellectual. They affect how we understand the world and our place in it in real life. For example, if future studies showed that time travel, or at least changing the flow of time, is possible in some situations, it would completely change how we think about cause and effect, and could have huge effects on technology, philosophy, and even ethics. If these problems can be solved, it might one day lead to discoveries that let us use time in ways that are only seen in science fiction right now. Proposed mechanisms for time travel. Ideas about how to travel through time have been a topic of interest in both science and philosophy for a long time. Theorists are looking into different ways that space-time could be changed to allow journey between different times. One well-known process is the idea of trekking wormholes, which are made-up paths in space-time that general relativity says should exist. In theory, a wormhole could join two very far-apart points in space and time, letting an item move from one place or time period to another almost instantly. But for a traversable wormhole to stay stable, it seems to need strange matter with negative energy density, which is a type of matter that hasn't been seen for sure yet. In spite of this, theoretical models based on Einstein's field equations, like the Morris-Thorne metric, make it possible to carefully look into the idea of time travel through wormholes. Another mechanism under consideration is the exploitation of closed time-like curves, CTCs. These are paths through space-time that loop back on themselves, meaning an object following such a path could theoretically return to its own past. Certain solutions to the equations of general relativity, like those associated with rotating black holes described by the Kerr metric, suggest that CTCs might exist under specific conditions. In these scenarios, an object might enter a region of space-time where the normal sequence of cause and effect is disrupted, allowing for backward time travel. The existence of CTCs raises significant challenges, such as the infamous grandfather paradox, yet various proposals, including the self-consistency principle, argue that the universe's physical laws might inherently prevent contradictions by ensuring that any events occurring along a CTC are consistent with history as already observed. Quantum physics also suggests possible ways to move through time. Quantum entanglement has been suggested by some experts as a way to make communication easier, or even to move through time. In these models, the non-local links that are a part of entangled systems might make it possible for information to be sent across time. Quantum entanglement has been proven to exist in the real world, but its effects on time travel on a large scale are still very much a guess. Other quantum-based ideas use the idea of retrocausality, which says that things that happen in the future can change what happened in the past. Within these kinds of models, the usual one-way flow of time could be rethought, and there might be times when the line between the past and the future becomes porous. Most people in the field of physics don't agree with these ideas, but they do spark heated discussion about the basic nature of time and cause. New ideas are coming up that blend conventional and quantum ideas. One way to look at it is by thinking of time as something that just happens. Quantum gravity theories don't see time as a fundamental variable. Instead, they see it as something that comes from the interactions and correlations of more basic quantum states that don't change. In this context, changing these basic quantum processes might allow for a type of time engineering in which the flow of time is changed or rearranged. Such a radical idea says that if we could figure out how quantum mechanics affects space-time, we might be able to control or handle its emergent qualities, which could lead to controlled time travel. Some suggestions also look at the idea of using high-energy processes, like those that happen in particle reactors, as possible ways to change the past or present. Particles are sped up to speeds close to the speed of light in these tests, and time dilation effects make their lives longer. Drawing conclusions from these events, thinkers have thought about the idea of creating places where time can be changed on a very large scale. Even though this kind of management isn't possible with the technology we have now, these ideas open up interesting new areas of study in high-energy physics and advanced engineering. From wormholes and closed time-like curves to quantum retrocausality and emergent time engineering, all of these suggested methods have a lot of theoretical and practical problems that need to be solved. For example, even if strange matter with the right qualities to support a wormhole were found, there would still be questions about how to control, navigate, and keep people safe in such a passage. In the same way, the math behind CTCs gives us good answers for problems in general relativity. But when we move from mathematical possibility to physical reality, there are many problems that still need to be solved, like how to keep causality and avoid paradoxes. Quantum methods give us an intriguing look into different ways that time works, but they are still a long way from creating the right conditions for large-scale time travel. This doesn't change the fact that these hypothetical processes are important thought experiments that help us learn more. They make us think about the problems with our current theories and ask if the fabric of space-time is really as flexible as our models say it is. Finding ways to move through time continues to be a topic of interest in both science and philosophy. This is true whether the search is for quantum gravity, high-energy physics, or new engineering solutions. These studies not only help us understand time better, but they also push us to think outside of the limits of reality, which opens up options that were once only possible in science fiction. The illusory nature of time, psychological perception of time. When we think about it, how fast or slow time seems to go by is a very unique and changeable thing, not at all like the way a clock ticks. According to psychological study, time perception is not a set, objective measure. Instead, it is a dynamic construct created by our brains that is affected by many things, such as mood and attention. One main way our brains handle time is through internal pacemakers, also known as clocks. These help coordinate regular activities like breathing and heartbeat, and give us a sense of how long something lasts. But these brain clocks aren't perfect. Mental states, emotional states, and outside inputs can change how accurate they are. For example, when we are really into a job, time can seem to go by very quickly. On the other hand, when we are bored or anxious, time can seem to drag on and on. Many psychology studies have asked people to guess how long a stimulus or gap lasted in order to look into this effect. Researchers have found over and over that our sense of time is skewed by things like how strong the trigger is, how much attention we pay to it, and how we feel at that moment. How we feel about time is very important to how we see it. When we are feeling strong emotions, whether they are good or bad, time seems to move more slowly because our brains are using more energy to understand them. It is thought that this effect is an adaptable process that helps us respond better to events that could be dangerous or important. For example, people often say that time seemed to slow down during a scary event like a car accident, which allowed them to process important information that could have saved their lives. In low arousal states, on the other hand, like when you're doing routine or boring things, time may seem to move faster because your brain isn't as busy understanding how fast time is passing. Cognitive neuroscience studies have used a variety of methods, such as behavioral trials and neuroimaging techniques, to look into how parts of the brain, like the prefrontal cortex and basal ganglia, affect how we sense time. It is thought that these parts of the brain combine sense information with memory and attention, building our experience of time. Attention is another key factor influencing time perception. When we focus intently on a task, the brain processes a wealth of information, leaving fewer cognitive resources available to monitor the passage of time, which can result in time feeling compressed. In contrast, when our attention is divided, or when we are not fully engaged, we tend to become more aware of the ticking clock, and time seems to stretch out. This interplay between attention and time perception has significant implications not only for understanding human cognition, but also for the design of environments and technologies. For example, in high-stress professions such as aviation or surgery, training programs often include exercises designed to enhance temporal awareness and improve decision-making under time pressure. In addition to the way our brains work, cultural and social factors also affect how we experience time. Different cultures have different ways of thinking about time. Some stress being on time and being efficient, while others make plans more fluidly and flexibly. Through learned habits and standards, these cultural views can change how people act, and even how their brains process time. How people organize their work, play, and sleep, among other things, affects how they experience time every day. In addition, our own emotions and expectations play a big role in how we feel connected to things. The brain is always putting together things from the past, the present, and the future that we hope will happen. This creates a story flow that makes sense of time. This merging doesn't just happen, it changes how we think about the current moment. This supports the idea that time, as we experience it, is not a basic part of the physical world, but something that comes from complex mental processes. The idea that time might be a trick has very deep intellectual implications. In the event that our brains create how we experience time, then the objective physical aspect of time, as explained by physics, might be very different from how we experience time. This difference makes us wonder about the nature of reality. Is time a fundamental part of the world? Or is it something our minds make up for a reality that doesn't change? Philosophers, neuroscientists, and physicists are still talking about these kinds of arguments, which leads to interdisciplinary study that tries to find common ground between these seemingly different points of view. In laboratory settings, experiments that manipulate time perception have provided further insights. Techniques such as sensory deprivation, where participants are isolated from external stimuli, have shown that the brain's internal clock can either speed up or slow down dramatically, leading to altered states of consciousness. Additionally, pharmacological studies indicate that certain drugs can modify time perception by affecting neurotransmitter systems, further illustrating the malleability of temporal experience. These experimental findings underscore the idea that our sense of time is highly dependent on the brain's current state and can be influenced by both internal and external factors. Neurological construction of time. The brain doesn't just idly record the ticking of an outside clock, it actively creates our sense of time through a complicated web of neural processes that work together. Neuroscientific study has shown that our sense of time comes from the combined activity of many parts of our brain. Each of these parts processes, stores, and retrieves temporal information. Neural oscillations, synchronization across distributed networks, and the blending of sense inputs with internal states are some of the most important parts of this way of thinking about time. Neural oscillations, which are regular patterns of electrical activity seen in different parts of the brain, are at the heart of processing time. These oscillations, which happen at speeds ranging from slow delta waves during deep sleep to fast gamma waves linked to higher cognitive processes, keep track of time in the brain. They help separate continuous lines of sensory information into separate windows of time, which are the building blocks of how we experience time. For example, the theta rhythm, which is usually seen in the hippocampus, is thought to be very important for storing and retrieving memories, connecting the past with the present and the hopes for the future. Synchronization of brain networks is also important for a unified temporal sense, along with oscillatory activity. Electroencephalography, EEG, and magnetoencephalography, MEG, studies have shown that when oscillating activity in different parts of the brain is coordinated, it makes it easier to combine knowledge from different times. This synchronization is especially important when doing things that need exact time, like playing an instrument or organizing a lot of different motor actions. It makes it possible for different parts of the brain that process different kinds of sensory information to talk to each other and make sense of time. The brain's ability to make sense of time depends on how attention and memory work together. The hippocampus and prefrontal cortex work together to control and watch the flow of temporal information. The prefrontal cortex is in charge of executive processes. Attention filters out some stimuli and makes other stimuli seem less important. It also changes how long things seem to last. Focused attention makes the brain use more of its resources to understand the details of an event, which can make time seem to move more slowly. On the other hand, time may seem to go faster when you are not paying attention. On the other hand, memory helps us understand time by connecting the present to things that happened in the past. The brain is always comparing new information with old memories to figure out how long things have been going on. This process shapes our sense of growth and continuity. The brain's predictive coding system is another important part of how time is built in the brain. This idea says that the brain is always making guesses about what sense information will be like, and then changing those guesses based on what it actually sees. This steady feedback loop helps make time flow smoothly by letting us guess what will happen next and changing how we see things accordingly. Predictive coding not only helps keep our experiences of time continuous, but it also affects how we feel like time is passing, how we feel like moments mix together as we go about our daily lives. Problems with how we perceive time shed more light on the neural bases of temporal experience. People with mental illnesses like schizophrenia, ADHD, and Parkinson's disease often have big changes in how they feel about time. For example, people with schizophrenia may feel like time is coming and going in pieces, which makes the present seem disorganized and confusing. In the same way, people with Parkinson's disease, whose dopaminergic systems are damaged, often say that time seems to move more slowly, especially when they are doing physical tasks. These changes give us important information about how our brains process time. They show how chemicals like dopamine help control our internal clock and change how fast we think time is moving. Neuroimaging studies have identified several key brain regions that are central to constructing the perception of time. The cerebellum, traditionally associated with motor control, has been shown to contribute to timing and coordination, particularly in tasks that require precise intervals. The basal ganglia, a group of subcortical nuclei, are implicated in interval timing and the regulation of temporal dynamics, and their dysfunction is often linked to disorders that affect time perception. The insular cortex, involved in integrating sensory and emotional information, also plays a role in how we experience time, particularly in emotionally charged situations where time may appear to slow down or speed up. New developments in neurotechnology have made it possible for scientists to change neural systems that control how we sense time. This is more proof that how we sense time is a brain creation. Transcranial magnetic stimulation, TMS, and deep brain stimulation, DBS, are two methods that have been used to briefly change the timing of neural rhythms. This has been shown to change how people experience time intervals in a way that can be measured. Not only do these experiments support theoretical models of how we sense time, but they also show hope for therapeutic uses that try to fix problems with how people in clinical groups process time. Consciousness and the subjective experience of time. The way we feel about time depends on how memory, anticipation, and the development of our mental understanding interact with each other. Time is not a set external factor. Instead, it is actively constructed by the brain. This is done by constantly combining past events with present sensory information and expectations for the future. This shifting of time creates the familiar flow of moments in which the past affects the choices we make now and changes our hopes for the future. This creates a continuous story that supports our sense of who we are and our sense of continuity. The role of remembering is at the heart of this lived experience. Our brains are always retrieving memories and experiences from the past and integrating them into the way we think and feel now. There is no idle replaying of recorded information in this retrieval process. Instead, there is an active reconstruction process that gives the past meaning and context. Memory helps us organize events in time, putting together a story from different sensory inputs that don't make sense on their own. The hippocampus, an important part of the brain for making and retrieving memories, is at the center of this process. Memory helps us understand cause and effect and how things change by connecting things that happened in the past to things that are happening now. Anticipation, on the other hand, is equally vital in shaping our perception of time. The brain is not merely a recorder of past events. It is a predictive machine that continuously forecasts future occurrences based on current stimuli and past experiences. This forward-looking capacity is driven by neural circuits in the prefrontal cortex and basal ganglia, which generate expectations and prepare us for imminent events. Anticipation fills the future with possibilities and, in doing so, contributes to the sensation of time flowing. When we look forward to an event, such as a celebration or a significant personal milestone, our internal clock seems to tick at a different pace, a phenomenon that underscores the fluidity of our temporal experience. When memory and anticipation come together, they create what is called the specious present. This is the short amount of time when our conscious experience is united. This time frame isn't set in stone. It changes based on things like brain load, mental state, and attention. For instance, when we are very focused or emotionally charged, the false present can seem to grow, letting us feel nuances more fully. When you're bored or distracted, on the other hand, time can seem to slip away without you noticing. This range of changes shows that how we think about time is less about an objective, straight line, and more about how our minds process and make sense of information. From a philosophical point of view, these findings call into question the idea that time is an essential and objective part of the world. Instead, they support the idea that time may be a cognitive construct, something that comes about when the brain tries to order experience. Philosophers like Immanuel Kant agreed with this point of view. He said that time and space are not things that exist apart from our awareness, but rather forms of intuition that shape how we experience the world. From this point of view, time is not something that happens out there in the world. Instead, it is a part of how our thoughts make sense of the chaos that comes from our senses. Neuroimaging studies have provided further insights into how the brain constructs our temporal experience. Functional MRI and EEG studies reveal that various brain regions, including the prefrontal cortex, basal ganglia, and insular cortex, are actively engaged when we estimate the duration of events or when we recall past experiences. These studies demonstrate that time perception is distributed across multiple neural networks, each contributing different aspects such as attention, memory, and sensory integration to the overall experience of time. Moreover, disruptions in these networks, as seen in neurological disorders like schizophrenia or ADHD, often lead to significant distortions in time perception, reinforcing the idea that our experience of time is a delicate, brain-mediated process. Our emotional experience of time also has big effects on how we think about free will and making choices. We feel like our actions and choices will follow an expected path when we think of time as a steady flow. However, if time is purely a product of our minds and is fluid, changeable, and based on our inner states, then it makes us wonder if our decisions are really set in stone. For a long time, philosophers have argued about whether time and events happen automatically or whether the future is truly open. Memory, anticipation, and sensory experience all change over time. This suggests that the future is not a set thing, but a possibility that is always changing based on our actions and hopes. A clear pattern. But if time is essentially a creation of our consciousness, fluid, flexible, based on our internal states, it begs problems about the deterministic character of our decisions. Philosophers have long argued whether there is actual openness in the future, or if the passage of time and the development of events are preordained. The dynamic interaction of memory, expectation, and sensory experience implies that our expectations and behavior affect the continually changing potential that is the future, rather than a set object. Different situations can have a huge effect on how people view time. People who do practices like mindfulness and meditation, which change their attention and awareness, often say that they have a deep change in how they see time. They may say that it seems to slow down or even stop. These events suggest that time as we experience it might be able to be changed knowingly, which adds to the idea that time is created. Emerging technologies and experimental approaches, advances in time measurement. Recent technology advances have made it much easier to measure time with a level of accuracy that has never been seen before. This has shed new light on how complicated temporal dynamics are. Ultra-precise atomic clocks have achieved accuracy levels of parts per quintillion. They depend on the steady movements of atoms such as cesium, strontium, and ytterbium. Not only are these clocks necessary to keep our modern technology, like satellite navigation and phones, working properly, but they are also very useful for testing basic physics ideas, like what relativity says about time and space. Gravitational time dilation has been directly proven by tests that compare atomic clocks at different heights. Clocks in stronger gravitational fields tick more slowly than clocks in weaker fields. These kinds of studies show that how we think about time is strongly linked to how things are in space right now. This is very important to keep in mind when we're looking into time on a cosmic scale. Advances in quantum clock technology have further pushed the envelope of precision timekeeping. Quantum clocks, which exploit quantum entanglement and interference effects, are expected to surpass the performance of traditional atomic clocks. By harnessing the unique properties of quantum mechanics, these devices could provide even finer measurements of time and enable new experimental tests of the interplay between quantum phenomena and gravitational effects. Such experiments are at the forefront of research in quantum gravity and may eventually help to resolve long-standing questions about whether time is a fundamental aspect of reality or an emergent property arising from more primitive quantum interactions. The addition of artificial intelligence, AI, and machine learning to the process of measuring time is another big change. AI programs can look through the huge amounts of data that networks of atomic and quantum clocks produce and find small errors and trends that people might miss otherwise. We need to be able to do this in order to improve our models of time and look for small changes in time that might point to new physics. AI-driven research has been used to test the security of atomic clocks over long periods of time, finding possible deviations that could be caused by environmental factors or even physical processes that we don't fully understand yet. These improvements in how we measure time also have big effects on the study of the universe. As part of space missions and observatories, high-precision clocks are being used to measure how fast the world is expanding and to test the forecasts of general relativity. Scientists can find small changes in the flow of time caused by gravitational forces and the growth of the universe because these clocks are so well synchronized and accurate. These kinds of data can help us understand things like dark energy and how the cosmic web has changed over time by showing us how time behaves in very harsh settings. Quantum devices that can pick up on very small changes in gravity fields are another example of a new way of doing experiments. With the help of very accurate clocks and these sensors, scientists can look into how local space-time curvature affects time. As these technologies keep getting better at measuring things, they might one day let us find strange events in time on a cosmic scale. This would support theories that say time is something that appears or changes over time. The refinement of time measurement technologies is not just about achieving greater precision. It is about opening up new avenues of inquiry into the fundamental nature of time itself. With ultra-precise atomic and quantum clocks, scientists are now in a position to test whether the passage of time is affected by factors that were previously beyond our observational reach. These advances have the potential to challenge our traditional Newtonian notion of time as an absolute, unchanging parameter, and instead support models in which time is intimately linked to the dynamic processes of the universe. Future technologies for probing time anomalies. Computer programs that use artificial intelligence, AI, and machine learning to look at the huge amounts of data that very accurate clocks and space-based observatories make is one of the most interesting areas of research. AI systems can sort through petabytes of timing data and find tiny trends and outliers that could mean that the flow of time is changing in ways that aren't predicted by traditional models. For example, small changes in how clocks are synchronized across different gravity potentials, or sudden changes in the timing signals from faraway astronomical events, could show temporal phenomena that were not known before. AI systems can help us understand time better by constantly learning from and changing to new data. This will help connect what we think we know about time with what we actually see. Quantum sense is another cutting-edge device that could change the way we think about time. It is very easy for quantum devices to pick up on changes in electromagnetic and gravitational forces because they use quantum entanglement and superposition. These sensors can pick up on very small changes in the curve of space-time. This gives us a direct way to look into time anomalies that might happen in very bad situations. Quantum gravimeters, for example, are being made to measure very small changes in Earth's gravity field. These changes could be tied to changes in the flow of time in certain places. As these sensors get better, they might be used on space trips to keep an eye on cosmic events. This would give us information about how time works in different parts of the world. The convergence of AI and quantum sensing opens up the possibility of real-time monitoring and analysis of cosmic time anomalies. Future space missions, equipped with networks of quantum clocks and quantum sensors, could provide continuous, high-resolution maps of temporal variations across different gravitational environments. These platforms could be strategically placed on satellites, space stations, or even on the lunar surface to compare time measurements across a wide range of conditions. By correlating these data with observations from astrophysical surveys, scientists could identify subtle discrepancies between predicted and observed time flow, potentially uncovering new physics at the intersection of relativity and quantum mechanics. Progress in high-energy physics studies, especially those using particle reactors and deep space probes, might help us learn more about strange events in time. By speeding particles up to almost the speed of light, it is possible to learn more about how they behave when time slows down very much. New detectors and data collection systems are making it possible to watch temporary events with a level of accuracy that has never been seen before. Not only do these studies test what relativity says should happen, they also test ideas that say our understanding of time changes at high energies or in strong gravitational fields. On the theoretical side, new experimental paradigms are being developed to investigate whether time is an emergent phenomenon rather than a fundamental parameter. Researchers in quantum gravity and cosmology are working on simulations and analog experiments that mimic the behavior of spacetime at the Planck scale. These experimental setups ranging from tabletop experiments using ultra-cold atoms to large-scale observations of cosmic microwave background anomalies, aim to explore how time might arise from more basic, timeless quantum processes. Such experiments could eventually shed light on the possibility that the continuous flow of time is a macroscopic illusion, emerging from the collective dynamics of a discrete, underlying substrate. Along with these experimental breakthroughs, it is also important to work together on foreign projects. Efforts like the European Space Agency's planned trips to test the effects of gravity and relativity in deep space, and the ongoing growth of global timekeeping networks, will give us a more complete picture of how time works at all sizes. With the help of shared databases and cross-disciplinary research groups, these projects want to get astrophysicists, quantum theorists, engineers, and computer scientists to work together more. This way, new technologies can be used to find out more about the most mysterious parts of time. As our ability to measure time anomalies improves, so too does our capacity to test the limits of existing theories. Discrepancies between theoretical predictions and experimental data could point to new physics, potentially revolutionizing our understanding of time and opening up possibilities for practical applications. For example, if future experiments reveal consistent anomalies in time flow that cannot be accounted for by current models, it may indicate that additional factors, such as dark matter interactions or quantum gravitational effects, play a role in shaping temporal dynamics. Alternative theories and future directions: the block universe versus presentism versus growing block theory. Eternalism is another name for the block universe theory, which says that events from the past, present, and future all exist at the same time in a set four-dimensional space-time fabric. Each moment is equally real, and the flow of time is a fiction, something that people think about rather than something that is real. Time in a block world is just another dimension, like the dimensions of space. The way we experience time passing is just how our awareness moves along this fixed landscape. Presentism, on the other hand, says that the only real thing is the current moment. This way of thinking says that the past doesn't exist anymore, and that the future hasn't happened yet. Presentists say that the world we experience is temporary, and that time is inherently important because only the present is meaningful from a philosophical point of view. This view fits with how we naturally think of time as a flow, where things keep happening and then becoming less important. The growing block theory is a view that falls in the middle of these two points of view. From this, it seems like the past and present are real, but the future is unknown and won't exist until it does. According to this model, the block of time keeps growing as new events happen. This keeps track of the past while keeping the future open to options. This theory tries to make sense of the fact that the past is set and the present is changing. It does this by giving us a way to think about both the consistency and change that are part of experiencing time. Each of these ideas gives us a very different view of how time works, which has huge effects on how we think about reality. The block universe's idea of timelessness goes against the very idea of time passing, saying that our experience of a now that flows is just a mental trick. This point of view makes me think about free will and fate, because it says that everything that happens in time is set in stone and can't be changed. Some people disagree with the idea that all times are equally real, because then it becomes impossible to make decisions or change outcomes, which would result in a world where the future is as fixed as the past. Conversely, presentism stresses the singularity and importance of the current moment. Declaring that only the now is genuine helps us to more intimately relate with our daily time and change experiences. This perspective does, however, also provide difficulties, especially in terms of harmonizing the subjective immediacy of the present with the objective measures of time given by physics. Presentists have to deal with how to interpret the strong empirical data for time dilation and space-time curvature in a framework in which just the present has ontological value. The growing block. Theory aims to bridge the distance separating the extremes of presentism from immortality. It respects the perception that the present is dynamic while the past is set. From this perspective, The block of time is dynamic and always growing as fresh events happen. This model presents a convincing approach to grasp our perception of the passage of time and the developing history. Still, it begs philosophical questions as well. For example, what decides the direction of block development if the future is not yet real? And how should we explain the seeming continuity of experience if the future is open and uncertain? Philosophical and scientific implications of time as an illusion. Philosophical research and scientific discoveries are making us question the idea that time is an absolute linear path from the past to the future. This suggests that time may be more of a construct than a fundamental part of the world. Philosophers like Immanuel Kant said that time is not something that exists apart from how we see it. Instead, they said that time is a framework that our thoughts use to organize our experiences. Modern physics has supported this idea, especially Einstein's ideas of relativity, which show that time is related to how fast a viewer is moving and the gravitational field they are in. So, what we think of as a steady flow of time might actually be a trait that comes about when basic physical processes combine in complicated ways. Now that we've looked at time differently, we might think that time is not a separate thing, but rather a result of how information is processed in the world. The idea that time is not real makes us question not only how our physical theories are put together, but also how we understand what we see and feel every day. For example, when we think of the present as a separate time, this could just be our brain's way of breaking up a continuous, undifferentiated state. The way that memory, expectation, and sensory information interact with each other adds to the idea that our brains make time seem real by putting order into the chaos of raw data. So, the idea of time may have a lot to do with how the brain has evolved over time, acting as a useful tool for making decisions and staying alive rather than a window into an objective outside world. This view allows for a lot of cross-disciplinary research, and philosophers, neuroscientists, and physicists can work together to learn more about how time really works. The idea that time might not exist has huge effects on many different areas of study. In cosmology, realizing that time may not be a basic background but an emergent feature changes how we think about the past and future of the world. If time is made instead of being natural, then the story of how the universe evolved from the Big Bang to cosmic inflation and now to the expanding universe may need to be rethought. The ideas of cosmic time and the arrow of time are connected to the rise of entropy. These ideas may be more about statistical and informational processes than about a straight line through time. In quantum physics, studies that show time dilation and the relativity of simultaneity show that time behaves in ways that are different from what we normally think it does at very small scales. Some ways of understanding quantum physics even say that time might come from more basic, timeless quantum states. This could point to a world where information, not pre-existing temporal dimensions, make up the fabric of reality. These new ideas about human awareness suggest that how we remember, look forward to, and feel like our lives are always going on may be the result of cognitive processes that have evolved to give structure to a world that is really timeless. The idea that time is an illusion opens up exciting new areas of study for the future. It encourages methods that combine philosophy, neuroscience, and physics. In the future, researchers might work on improving models of time as something that just happens, combining ideas from quantum gravity with cognitive science to find out how the brain creates experiences of time. New developments in very accurate timekeeping, like quantum clocks and AI-powered data analysis, will help us see the small changes in how time flows in different places, from labs on Earth to the farthest reaches of space. Experiments that look at how people perceive time when they are in different states, like when they are high on drugs, meditating, or not having any senses, could help us learn more about how temporal illusion works in the brain. Observational astronomy and cosmological models are also helping us learn more about how time works on a cosmic scale, especially in harsh places like near black holes, or when the universe was just starting to grow very quickly. It might be possible to close the gap between how time is measured objectively and how people experience it subjectively through joint research projects that bring together theoretical physicists, neuroscientists, and philosophers. By encouraging conversations between people from different fields, we can make models that cover more ground and include both the physical and subjective parts of time. These efforts might finally cause a paradigm shift in how we think about time, changing it from something that seems to be a natural dimension to something that is made up of complex relationships between matter, energy, and awareness. Cultural and social dimensions of time. Time isn't just a physical or biological thing. It's also a deeply cultural and social idea that shapes how people live, behave, and organize society. Over the course of history, different cultures have understood and counted time in ways that reflect their unique environments, spiritual beliefs, and technology advances. The way we understand and experience time is strongly connected to our cultural history and social practices. This is true for both old agrarian societies that use cyclical calendars and modern industrialized societies that use precise timekeeping systems. This part talks about how cultural norms, social routines, and new technologies have changed the way we think about time. It shows how objective measures and subjective experience are always changing and interacting with each other. Looking at how different societies organize and use time, from work and play to rituals and digital interactions, helps us understand how time shapes not only our daily lives, but also our larger sense of who we are as a society. The way people think about time has changed over time based on their surroundings, technology, and spiritual views. In old societies, time was often seen as a cycle instead of a straight line. For instance, a lot of native cultures saw natural patterns, like the seasons, the moon, and the rhythms of farming, as very important to their way of life. In these cultures, time wasn't just a series of events. It was a wholly repeating thing that was closely linked to the cycles of life and nature. As people tried to keep track of time and make rituals out of these repeating cycles, early timekeeping tools like sundials, water clocks, and early diaries were made. As societies progressed, so did the ways they kept track of time. Egypt, Babylon, and Mesoamerica were able to plan their farming better when they made more accurate calendars. These calendars also showed how important time was in religion and spiritual practices. Many of the events on these calendars, like holidays, solstices, and other celestial events, had mythological meanings. This fed the idea that time was a holy order that the natural world had to follow. As societies grew more complicated, time changed from a natural pattern to something made up by people. Standardized calendars were first used in ancient Rome and then in medieval Europe. They showed a move toward a more organized, straight view of time that helped with running the government, the economy, and religion. This change over time shows that even though time comes from nature, it has always been connected to human society and beliefs, which affects not only how we measure it, but also how we feel it passing. In modern society, time is deeply embedded in our social fabric, structured by cultural norms and economic demands. The Industrial Revolution marked a pivotal moment in the social construction of time. With the rise of factories and mass production, time became a commodity measured in precise units, hours, minutes, and seconds, dictating work schedules and organizing daily life. The regimented workday, the introduction of time clocks and standardized schedules not only increased productivity, but also redefined personal relationships with time, transforming it into something that had to be managed, optimized, and often strictly adhered to. However, leisure and traditions helped to smooth out this rigidity. Many cultural and social practices, from religious holidays and observances to shared meals and family get-togethers, honor the way time goes around and around. They provide a break from the fast-paced modern life. People use these social routines as anchors in their daily lives. They give people time to stop and think, which helps them connect with larger culture stories. In some countries, life moves more slowly because they value great experiences and spending a lot of time with family or community. In other cases, the fast pace of life in cities shortens time, creating a sense of urgency that can both spur new ideas and make people feel stressed. Different countries have very different ideas about how to tell time. While being on time and getting things done may be important in the West, many Eastern cultures have a less rigid view of time. Instead of tight adherence to plans, they focus on unity and the dynamics of relationships. Not only are these differences just habits, but they also affect how people in a community work together, make choices, and value their experiences. The way people think about time affects everything from how well people do in life to how productive the economy is. This shows how deeply our shared view of time affects society as a whole. Digital technology and global connections have changed the way we feel and use time a lot in the last few decades. With the rise of the internet, apps, and social media, people can talk and share information much more quickly than ever before. Because of this, time feels both sped up and broken up. Things happen quickly, one after the other, but our attention is always being split between several digital streams. As people try to keep up with the speed at which information flows and the demands that they must respond right away, this digital speeding can make them feel rushed and anxious. At the same time, technology has enabled us to measure and manage time with extraordinary precision. Modern devices, from atomic clocks to time synchronization protocols on the internet, ensure that our global networks operate seamlessly. However, this precision also brings with it a paradox. While our technological systems are governed by extremely accurate and deterministic measures of time, our subjective experience of time remains fluid and malleable. The constant bombardment of digital stimuli can alter our internal clocks, sometimes leading to a phenomenon known as time compression, where hours seem to pass in what feels like minutes, and other times causing periods of boredom when the digital noise subsides. The globalized nature of technology has introduced new cultural dimensions to time perception. Virtual workspaces, online communities, and remote learning environments blur traditional temporal boundaries, allowing for asynchronous interactions that transcend local time zones. This has led to innovative approaches to scheduling and time management, but also challenges traditional notions of punctuality and temporal order. In the future, new technologies like virtual reality and augmented reality could change even more how we think about time by giving us engaging experiences that can change how we think about length and order. As these tools improve, they might give us new ways to change how we feel about time, which could have uses in mental health, education, and fun. Ultimately, the interaction between exact technological measurement and the subjective nature of how people see time is an interesting look into how our idea of time is being built and changing in the digital age. Time has long been an important inspiration for artists, writers, and singers, leading to a wide range of creative works that capture its mysterious and always changing nature. Time isn't just counted or defined in art and writing. It's lived, changed, and reimagined, showing how memory, anticipation, and perception are deeply connected. Visual artists use symbols, color, and shape to capture the beauty of passing moments. Writers, on the other hand, play around with story structure to bend, stretch, and even reverse the flow of time. By changing the speed and rhythm, musicians create the heartbeat of time, taking viewers on an emotional journey that mirrors the changing and cyclical aspects of time. This part goes into detail about how different creative fields understand and reflect the meaning of time. It shows how our internal sense of time is connected to how time is shown in art. Modern artists have pushed these limits even further by using new methods to question how people usually think about time. In Salvador Dali's bizarre settings, for example, clocks that are melting are often used as a striking visual metaphor for how time is fluid and personal. In these works, time isn't shown as a rigid chain of events, but as a flexible, almost dreamlike state. This is meant to show how feelings, memories, and the inner mind can change how we see time. In the same way, the Cubist movement broke down scenes and items into different points of view breaking up time and space into a single, complex picture. This method lets people see time as a layered structure, where different moments appear at the same time, instead of going in a straight line. Sculpture and installation art have also offered unique insights into the representation of time. Kinetic sculptures, which incorporate movement as an integral element of their design, allow audiences to witness time's passage in real time. These works often rely on mechanical or natural forces, such as wind or water, to create continuous motion, symbolizing the relentless, ever-present flow of time. Installations that incorporate digital media and interactive components further blur the boundaries between past, present, and future, engaging viewers in a dialogue about how technology reshapes our experience of time. The use of time-based media in art, like photography, film, and performance, has made it easier to record and change temporal experience. Artists who work in these areas can arrange pictures in a certain order, add layers of meaning, and play around with time, which gives us new ways to think about and experience it. This moving image makes people think about not only how to measure time objectively, but also how to measure it subjectively, emotionally, and existentially. Time in literature, narrative structures, and temporal fluidity. Literature has long been a good place to rethink time because it uses story patterns that don't follow a normal, straight order. Different types of non-linear stories, fragmented tales, and overlapping periods have been used by authors to show how complicated and often fluid temporal experience is. The way stories are put together in many modern and postmodern works is similar to how people think about time. The past, present, and future are all mixed up, and the lines between them are not always clear. This method makes time seem less like a steady flow, and more like a collection of moments that can change, overlap, or even go backwards. One classic example of temporal fluidity in literature is the stream of consciousness narrative, which attempts to capture the continuous flow of thoughts, memories, and sensations as experienced by a character. Writers such as James Joyce and Virginia Woolf employed this style to break away from traditional narrative constraints, thereby offering a more authentic representation of human consciousness. Their work reveals how memory and perception can alter the sense of time, making it seem elastic and subjective rather than fixed and objective. Non-linear narratives in literature, where events are not recounted in chronological order, serve to destabilize the reader's perception of time. In novels such as Kurt Vonnegut's Slaughterhouse-Five or Gabriel Garcia Marquez's 100 Years of Solitude, the sequence of events is deliberately disrupted, prompting readers to reconsider the nature of cause and effect. These narratives invite an exploration of time as a construct that is as much about emotional resonance and thematic depth as it is about chronological order. Flashbacks, hints, and broken-up stories are also used to explore the idea of temporal flux. Authors weave a tapestry where the past, present, and future all live at the same time by moving between different stages of time. This way of telling a story not only makes it more interesting, but it also shows how unclear our own experiences of time are. The story turns into a living interaction between memory and hope, where the past is talked about and how it affects the present and how it makes us feel about the future. Changing the order of events in a story also has deep psychological implications. It questions the idea that time moves in a straight line and brings up issues of fate, free will, and how changeable human experience is. People who read literary study are pushed to think of time not as a fixed structure, but as something that can change and adapt to the way people think and feel. This point of view fits with current psychological and scientific discussions about whether time is a real thing in the world or just something our minds make up. Music, rhythm, and the embodiment of time. Music is a unique way to experience time through your senses, turning the abstract into an emotional, physical trip. When you listen to music, you can feel and measure time at the same time through rhythm, pace, and tune. The framework of musical pieces is based on repeating patterns and changes that are like how time goes in cycles. One example is the steady beat of a drum or the pulsing rhythm in a dance track. These sounds organize our sense of time so that we can experience it as a set of repeated intervals. This steady pattern in music rhythm is like the ticking of a clock, but it has creative changes that make you feel different emotions and speed up or slow down. Beyond mere rhythm, music often plays with the notion of time itself. Composers have long experimented with tempo changes, syncopation, and polyrhythms to create dynamic shifts that make time feel elastic. In classical music, movements may vary dramatically in speed, from the languid adagio to the frantic presto, guiding the listener through a range of temporal experiences within a single piece. In modern and experimental genres, time signatures are often broken or manipulated, challenging conventional expectations and encouraging listeners to reimagine the passage of time. This manipulation of musical time can evoke feelings of nostalgia, anticipation, or even disorientation, highlighting how our perception of time can be fluid and context-dependent. Music's ability to hold time is not limited to its rhythmic parts. Harmonic progression and melodic development also help tell a story of time by gradually playing out as themes are introduced, changed, and played again and again in a piece. This development gives a sense of time progress, like a story that changes over time. It invites listeners to go on an inner journey where each note and chord is a piece of a bigger time puzzle. The interplay of memory and anticipation in music further deepens our experience of time. Familiar tunes can evoke vivid memories, transporting us to moments in the past, while a sudden change in melody or a surprising modulation can generate anticipation for what comes next. This duality mirrors the cognitive processes underlying our perception of time, where the integration of past experiences and future expectations shapes our continuous sense of now. Consequently, music not only reflects our understanding of time, but also actively participates in its construction, engaging our emotions and intellect in the unfolding of a temporal narrative. The way that memory and expectation interact in music makes our sense of time even more complex. We can vividly remember times in the past when we hear familiar tunes, and we can't wait for what's next when we hear a quick change in rhythm or a surprising modulation. This two-sidedness is like how our minds work when we think about time. Our sense of now is formed by combining memories from the past and hopes for the future. So, music not only shows how we think about time, but it also shapes it, involving our minds and hearts in the progression of a temporal story. Time may not be as fixed as it seems. Perhaps it's a dynamic construct shaped by our perception and the fabric of reality itself. What are your thoughts? Share them in the comments below. If this exploration sparked your curiosity, don't forget to like, subscribe, and spread the wonder. Thanks for watching.